Bismillahirrahmanirrahim. Exact and invariant solutions. Symmetry methods for differential equation. Exact analytical solution of ODEs and PDEs versus invariant solution using Lie symmetries. So we draw some comparison between the exact solution and invariant solution of ODE and PDEs in this lecture. Okay, exact solutions provide closed analytical form. Invariant solution remain unchanged under symmetry transformation. So what is the difference? Basically, exact solution satisfy the equation exactly, and that one condition is enough for the exact solution. But invariant solution have to satisfy two conditions. It has to satisfy the given equation as well as the symmetry transformation or symmetry generator. So the invariant solution is more restricted than the exact solution because it has to satisfy two conditions. One, the given equation, and the other, the symmetry condition. Lie group analysis is a systematic method for obtaining such solutions. So we use Lie symmetry method to find invariant solutions. So for these solutions, we need to find generators and the corresponding symmetry transformation, and then use the symmetry transformation to find the invariant solution of the given differential equation. An exact solution satisfies the differential equation identically. Useful in mathematical physics, engineering, and many other fields. Not only in these, many other fields. There are differential equations related to the social sciences and the economic sciences. So there the differential where we have the differential equation, system of differential equation, we can solve them exactly analytically, or maybe we can use the other methods to like symmetry method and find invariant solutions. So can be obtained analytically using integration, transformation, or symmetry method. So analytic solutions can have their own methods analytically, and you people know them very well. For example, for first order ODE, we have separation of variables, exact differential equation, variation of parameter, and for higher order homogeneous is a method in which the coefficient are homogeneous function of x and y. For higher order, we have reduction of order, variation of parameter, undetermined coefficient. So these are the methods we use to find the analytical solution of the given ODE or PDEs. Invariant solution are preserved under symmetry transformation. Lie symmetry reduce differential equation to simpler form. Reduction often transform PDE into ODE. So in the invariant solution, we have to satisfy two conditions. The solution should satisfy the given ODE or PDE equation and also the symmetry conditions. So invariant solution are restricted more restricted than the exact or analytical solution. Lie symmetry generator. So if we have ODE, so we have this type of Lie symmetry generator, xi for the independent variable and eta for the dependent variable. But when we have PDE, let's say we have PDE in three variables, u, t, and x, where t and x are independent variable and u is dependent variable. Then the generator takes this form. We have three function xi1 of t, x, and u partial by partial t plus xi2 of tx in u partial by partial x in eta of tx in u partial by partial u. So in this case we have three terms in three variables in the generators, while for ODE we have only two coefficient and two variables. What does symmetry transformation do? It maps solution of the given ODE or PDE into solutions. Okay, so quick example of ODE. We have this is an ODE, dy by dx or d by dx of y is equal to y over x. So we separate them and we have this is the general solution. This is the exact analytic solution. This is the exact analytic solution. So we solve it by separation of variable and we get exact analytic solution. That is analytic solution. ODE, this is simplest second order ODE, pre-particle equation, and this is the generator. You see this equation is invariant under this generator. When we apply it on this equation, both sides give us 0 and it satisfies. So it is the generator. In other words, this equation is independent of x. We not see x in this equation, and that is why partial by partial x is the Lie symmetry generator of the invariant solution. You see, we find the invariant. This is the invariant. So any any function of y is invariant of this this generator. But we see that simple y is also invariant of this equation, this generator. So if we find the exact solution of the differential equation, that is y is equal to c1x plus c2. So this is the analytic solution of the given differential equation. What is the invariant solution? Y is equal to, if I take y is equal to c2, we have two solutions, x and a constant. So the constant solution is an invariant solution of the given differential equation, because this solution satisfy this is invariant, satisfy the generator. This is invariant of the generator, also satisfy the given differential equation. So this is the invariant solution and this is the analytic solution. So this equation satisfy this equation. This solution satisfy only the differential equation, but this solution satisfy the given differential equation as well as the symmetry generator. It is invariant for the given symmetry generator. So for invariant solution, we have to satisfy whether it is the invariant of the given generator or not, also whether it satisfy the given differential equation or not. So this is solution of this differential equation, but it also is an invariant of this symmetry generator. So this is invariant solution and this is the analytic solution of the given differential equation. Okay, heat equation. So we have this similarity variable. This is a similarity variable, but let me write the corresponding generator. This similarity variable come from the generator 2t partial by partial t plus x partial by partial x. So let's see whether it is invariant of this generator or not. So apply this generator on the given variable eta, and this is 2t partial by partial t plus x partial by partial x and it is operated on this function which is x and t power minus 1 by 2. So it give me 2t. So when I differentiate this with respect to t, I have minus 1 by 2 and this 2t, and this is differentiated with respect to t, so this is x t power minus 3 by 2 and plus x. I will differentiate this, we have to differentiate this with respect to x, so only t by 1 by 2 minus 1 by 2. So you see this 2 will cancel with 2 as a minus sign, and when we add the power of t, that is t minus 1 by 2 left it, x plus xt minus 1 by 2. So they cancel and we get 0. So that means this is the invariant of this generator. So we directly write it without mentioning the generator, but this is the generator and this is the invariant, and any function of this this invariant is a solution of this differential equation. You can check it. So this is the invariant solution of this differential equation. Differentiated it with respect to t. Let's do it. If we succeed, we are interested to satisfy the equation. This is invariant, that one condition is satisfied. This is invariant for this generator, but whether it satisfies this sort of function satisfy this differential equation or not. So ut, so we have to differentiate this with respect to t, this one with respect to t, that means minus 1 by 2 x and t power minus 3 by 2 not x. We have to n of f of eta dash okay. Now we have to differentiate this function. I differentiated it with respect to t. Now I have to differentiate it with respect to x. So with respect to x, I will get t minus 1 by 2 f dash, and then again with respect to x, so that will give me t minus 1 by 2 is already there, and we have another one differentiating the inner function with respect to x. So we have another 1 by 2 here, and if double dash, so here is the x. Okay, so this is equal to t minus 1 f double dash. Now putting u double dash NUT in the given equation, we will get NODE. You see it. This equation. So we will quickly put it here. UT is minus 1 by 2 minus 1 by 2 x and t minus 3 by 2 f dash, and this is equal to t minus 1 f double dash. On simplification, it will give me an ODE of the type f double dash plus 1 by 2 and x t minus 1 by 2 f dash equal to 0. Simply an equation f double dash plus 1 by 2 eta. You see this is eta and f dash equal to 0. So we can put another function h dash plus 1 by 2 eta h is equal to 0. What h is? H is f dash. So solving this equation by, you see the integrating factor for it is integrating factor. So I am writing directly the integrating factor. Search out on the integrating factor. This is exponential eta square over 4. Exponential eta square over 4. So this equation, then give me, multiply with this eta square over exponential eta square over 4. This equation will take the form exponential eta square over 4 h dash plus 1 over 2 eta exponential eta square over 4 and h equal to 0. We see that this is d by d eta of exponential eta square over 4 h equal to 0. So from here we directly integrate and get eta square over 4 h is equal to a constant by integration. Okay, the remaining question we will solve over here. We know that what is h. H is f dash, so we will find h. So h is equal to constant e minus eta square over 4. Putting f dash over here minus eta square over 4. Now this is, I will leave it in the integral because you have to use some elementary calculus. This is eta square. It's not easy to integrate, but f is equal to C integral exponential minus eta square over 4 d eta and plus some other constant. This will be f. So this will be the solution if you succeed to find it, and you have to use some transformation over here, and you will be able to find. So that will be the invariant solution of this differential equation. So you see what the invariant solution. We find an invariant of a generator, so we find it here. That is the we check it here that this is the invariant of this generator. Now any function of it will be a solution, so we put it into the given PDE. The given PDE reduced to an ODE, linear ODE, and we try to solve it and find the solution. This will be the invariant solution of this PDE for this generator. Invariant solution of this PDE, which is the heat equation for this generator. So it has satisfied two conditions: invariance of this generator, also the degree. So the wave equation has this invariant, but for what generator? We have a generator X is equal to partial by partial T plus C partial by partial X. So this is invariant quantity for this generator. Simply you have to check it. X minus C T. So operate this on this, you will see a minus C from here. This is 1 and minus C, and from here it is plus C. So 0. So mean this is the invariant. This is the invariant of this generator for this differential equation, because this is the generator for this differential equation. You can check it. When you apply it on this, you will zero on both sides, so it satisfy this equation. Mean this is the generator of this equation. In fact, we have two generator, x1 which is partial by partial T, and x2 which is partial by partial X. So this is a sort of linear combination of these generator, and this quantity is invariant of this linear combination of these two generator. So any function of this invariant is solution of this equation. You can check it. You see, let's check it whether this function of the invariant is solution or not. So ut will give me f dash minus cf dash, and utt will give me c square f double dash. Now ux will give me only f dash, and uxx is f double dash. When we put it here, you see this is only the left side is this is c square f double dash is equal to the right side is c square f double dash. So mean this type of function satisfy this equation. That means this is the solution, but this is not the ordinary solution, it is the invariant solution of this differential equation for this generator. Okay, let's discuss another one. If we take another generator, let's say Y and that generator is a linear combination of that, but I am taking the linear combination of this type, partial by partial t minus c partial by partial x. So when you operate this generator on this quantity, this is minus, so plus it, x plus ct. So you see we will have c here and minus c here, and it is 0. So utx is equal to some g of x plus ct is again a solution of this differential equation. You have to check following these steps. You have to check that this is again a solution, and we have a D'Alembert solution of the linear combination. We have, so you see this is a okay, this is one invariant solution, this is second invariant solution, and if we take the linear combination, this solution is the forward moving wave, this solution is the backward moving wave solution, and if we take the linear combination of f x plus this is minus ct and g x plus ct is, this will be again solution of this differential equation. This is the D'Alembert solution, but this solution is not invariant solution of this generator and not invariant solution of this generator, but it is a solution of the both of the generator. One invariant come from one generator, the second invariant come from the other generator, so it is a combined invariant solution of these two generators, this one and this one. So this is a combined invariant solution per generator x and y, and it is the famous D'Alembert solution of the wave equation. So it satisfies these two generators as well as the given differential equation. Okay, invariant solution has many applications, so I write only 4 of them. Fluid dynamics, in fluid dynamics, about each paper have invariant solution. They reduce a system of very high nonlinearity and take the similarity transformation and reduce the PDE into ODE system, and then solve the PDE system and follow this procedure. But they take you see, this is the similarity transformation, this one, this is the similarity transformation, this is the similarity transformation. So this similarity transformation come from generators of the given differential equation, but when we see the paper of fluid dynamics, they take the similarity transformation by itself, no generators are there, they take the transformation and reduce the PD into OD and then solve. So there is a procedure behind the similarity transformation. You have to take generators of the given differential equation, PDE differential equation system, and use that generator to find the invariant, and then use that invariant to convert the PD into OD, like we did in the previous example number 3. The PDE goes into ODE and we solve the ODE. So in fluid dynamics is very much useful. In general relativity and black hole physics, invariant solutions are very much important, and quantum mechanics also use the invariant. The Schrodinger equations has invariant solutions, so there are generator of the Schrodinger equation, and there are symmetry transformation for that the generator of the Schrodinger equation, and we use the invariant concept for the Schrodinger equation to solve the Schrodinger equation. Non-linear dynamical system, so all the above are non-linear dynamical systems. So fluid dynamical, so when you derive a fluid dynamical system, they are non-linear. General relativity and black hole equations are non-linear. Quantum mechanics, Schrodinger equation is not non-linear, but for different potential it becomes difficult to solve the Schrodinger equation, so you have to find the invariant solution of the Schrodinger equation using the generators of the Schrodinger equation. What are the benefits of invariant solution? It reduces the complexity. In simple word, PDE goes into ODE. Reveal Hadal geometries. Provide exact analytical expression. Useful for non-linear models. So all of them has much time to talk on each of these, but this is very clear. You see one example, they reduce complexity of equation. So you have PDE, and the invariant technique give us a ODE of the PDE. That means it reduces complexity of the equation. Sometimes the non-linearity, you have non-linearity equation, but when you use the similarity transformation or symmetry method, the non-linearity goes into the linearity. That means the symmetry transformation linearize the given non-linear model if it is linearizable. So we conclude our lecture here. Exact and invariant solution are certain to modern mathematical physics. So exact solution are very important, but sometimes it is difficult to find exact solution of differential equations, so we come toward the symmetry method and find the invariant solutions, and at least we see some solution of the given phenomena. Lie symmetry method provides systematic reduction technique. Sometimes we reduce the order of differential equation using Lie symmetry. So instead of second order, we get first order, and it is easy to deal with the first order ODEs or PDEs. Application of symmetry method extend to science and engineering, and we discuss some of them in this video. If you learn something from the lecture, then help us to improve the series by liking the videos and comments on it. If there is something wrong, we have to communicate to correct them, and subscribe for